Hi everyone. Thanks for being back. Today our speaker is going to be Zhun Deng. He's an assistant professor who just actually started very recently at the University of North Carolina in Chapel Hill. Before this, he was a postdoc researcher with Tony Pitazzi and Richard Zemmel at Columbia. And he did his PhD in theory of computation group at Harvard, where he was advised by Cynthia, who's actually part of our collaboration here. He's doing a lot of research at the intersection of machine learning, statistics, and theoretical computer science. And currently, he's been interested in practical frameworks with theoretical guarantees to address like cutting edge issues for reliable learning and responsible computing. And so today he's going to be telling us about his research for responsible learning with quantile-based risk measures. Jun, yeah, it's all you now.
Okay, thanks for the introduction. Yeah, it's actually a long delay for this talk. It's actually I should deliver it last semester, but I had a medical issue. But yeah, it's lucky that I can make this today. And today I'm going to talk about the responsible learning with quantile-based risk measures. So, like modern AI, as we know, like it's very powerful and used everywhere in every critical area, such as medical care, self-driving cars, and building powerful chatbots. However, if we use modern AI in a careless way, it can cause a lot of problems. For instance, in medical care, some algorithms are found not actually paying attention to the minority groups, so patients in those groups actually cannot receive timely treatment. And in building the chatbot based on LLMs, some chatbots can even like encourage people to commit suicide. So there has been urgent concerns about the modern AI, and people have been trying to find ways to harness modern AI. Like for instance, in an open letter that is signed by a lot of research scientists, they actually advocate pause giant AI experiments so that people can have more time to think about what's going on and what will be the potential risk. So quoting from the letter, AI labs develop and deploy ever more powerful digital minds that no one, not even their creators, can understand, predict, or reliably control. So we actually want to find some frameworks that can help us deploy AI responsibly. So by saying responsibly, I mean that we want to deploy AI in a way that is safe, explainable, and aligned with societal values. I'm sure it's actually very familiar with familiarized by the people here. Yeah. So, however, like most of the AI work right now regarding responsible deployment, they are based on heuristics or just pure engineering techniques. So, from my personal view, I think that is not enough. Actually, regarding that, I think we actually should have some rigorous theoretical tools to help us to actually deploy modern AI in a more responsible way. So today's outline, I'm going to talk about some of the recent works we have been doing or like trying to build up some theoretical frameworks to help us to deploy black box models in a responsible way. So first, I will talk about distribution-free risk control. Actually, this is a rise from some statistical work that in conformal risk control. And then I will talk about like a model auto evaluation. How can we actually evaluate those models in a more efficient way so that we can ensure they have no problems, at least serious problems before we deploy them. Okay. So first, I will talk about distribution-free risk control. And here, like I want to emphasize what's wrong with the modern AI. Like even though we know that large language models are very powerful, they can be used everywhere. They can still output like very extreme outcomes from time to time. For instance, the examples I mentioned, the forehead, that's saying that they can. The chatbots built on large language models can output responses that encourage people to commit suicide or fraud. And I want to emphasize what is actually very hard here is that modern AI, actually, the models we are using are becoming increasingly complex. So models actually right now are becoming too complex to understand the inner workings. And sometimes we don't even have access to the model details. So those are not open source. So most of the time, we can only treat those fancy models as black box models. And however, we have already been deploying those black box models everywhere in basically every task we can imagine. So here is the question: is that how can we build like a rigorous framework to help us to regulate the black box models behavior? So today, first, I'm going to talk about, like in this part, I'm going to talk about a mathematical framework to help us to quantify the extreme outcomes. Then I will shed some light about like how to use them exactly to build a rigorous framework to regulate the behavior of black box models. So since I'm been talking about a chatbot, so I will use the chatbot as an example. Like people can ask questions to the chatbot, and the chatbot can output answers. And based on the quality of the answers, for instance, toxicity of the answers, they can incur different loss values. And those loss values usually could be measured by some off-the-shelf models such as Detoxify. Okay. For instance, if I ask the chatbot saying that how to relax after work, and the chatbot may answer like take a deep breath and then do some sports. So this is a perfectly appropriate answer. So it will only incur a very small loss. For instance, the L1 here, like indicated by the blue cross. However, when people ask another question, saying, for instance, I'm stressed out, what should I do? Like if the answer is saying that live with that, you loser. So this is actually not an appropriate answer. And this can incur actually a very large loss, that is the L2 here, that's indicated by the red cross. So from this example, we can see if we further impose a distribution, an underlying distribution for the questions, then it can actually lead to a loss distribution. So here, like actually by saying imposing a distribution, this is actually very natural in machine learning because people just train it in this way. Like this is just a natural way to think about it. So in order to quantify those extreme outcomes, actually what we need to pay attention to is the tail of the loss distribution. Okay, so we need to characterize the tail of the loss distribution. So there have already been a lot of concepts to help us with that. For instance, some concepts from mathematical finance say that the outcomes, for instance, value at risk. So this is basically just the quantile, and also like some concepts trying to quantify the average of the loss of the worst, 5% outcomes. For instance, this is called conditional value at risk. So this is those are all like a very well formatted concepts. And in order to express this in a mathematical framework, we need to introduce some notations. So actually, these are all established. I just introduced these concepts here in order for later use. So here, if we denote the loss as L, and then as we mentioned, we have a loss distribution. So we call the CDF as FL. So since we have a CDF, then we can naturally define our quantile function of loss that is defined in this way. So a CDF of the loss distribution can actually lead us to a quantile function of the loss distribution. Okay. So what I'm going to talk throughout this talk is regarding this important idea called a quantile-based risk measure. So this is actually a very rich family of risk measures. This actually not just including the tail measures I mentioned before. It also includes some natural measures like expected mean that we will encounter. So by choosing different weighting functions, like then we can get final scalar by integrated over the quantile functions. So this is basically a linear functional of the quantile function. And so for instance, if we choose the weighting function as 1, then it will give us expected mean. And if we choose as a delta function, it will give us the quantile, like the so-called value at risk. And the C bar is just some the piecewise functions. Okay. So in this talk, I will mainly focus on this linear functional of the quantiles, but actually in our work, we also mentioned some nonlinear function of the quantiles, such as Gini coefficients to measure the fairness stuff. And without loss of, like if we don't have ambiguity, then we will just use this shorthand that FQL as the functional in general. Okay, so after introducing this mathematical framework to actually capture the extreme outcomes. So the question is that how can we actually build a framework to regulate the behavior of black box models in order to avoid outputting those extreme outcomes? So this will follow from a rich line of work in statistics called conformal risk control. Actually, what they do is to treat a black box model, and then you have some extra parameter that you can fine tune or using the validation data that can help you to regulate the behavior of the black box models. However, what they do is just usually focus on standard prediction models, and they only consider intervals or expectations. So here, like in our framework, we want to introduce something that can help us to regulate the behavior of generative AI, and also we want to go beyond expectation and to control a much richer family of measures that we mentioned before. So to go back to the framework, I will first bring some examples here by further introducing some notations. Here, like as I mentioned before, if we have some question Z, we input to a model, like for instance, chatbot here, F, then we can get some response FZ. So based on the quality of FZ, it can incur some loss values. So it is denoted as LFZ here. So as I mentioned, if we have a question distribution, that is a distribution that Z is drawn from, then it can incur a loss distribution. So here, the idea is that how can we control certain quantile functionals for the underlying question distribution? So the idea is basically similar to multi-calibration, that we have some pre-given threshold, and we hope that by choosing some extra parameters, we can actually make sure the functional of the quantiles actually could be smaller than some previous given threshold alpha. So how can we do that for generative AI such as LLMs? Actually, let me first introduce the concept of prompt engineering. So this is actually a very prevalent concept of actually 1 or 2 years ago, actually. So this is called prompt engineering, is something that we want to design the inputs for LLMs to help to produce better outputs. So we want to manipulate a few prompts so that can help us to get better outputs. So here for prompts, I actually will only focus on system prompts instead of like individual prompts. So system prompt is something that embedded in the system that is actually fixed for all the questions. So this can include task descriptions or some instructions. For instance, if I'm building a chatbot, then I can input like the developer of the chatbot can actually input a system prompt saying that please be friendly when you respond. So that whenever customer asks a question, then hopefully the customer can get a better answer that in a more friendly way. Okay. So here the chatbot is basically just built upon some black box models, that is the LLMs, and also some specific embedded like, system prompts. Okay. So usually, like these system prompts, they are chosen by some heuristics, and they are fixed for all the questions. So this is what in previous like AI work they have done. Okay. So in this framework, we want to choose these prompts in a more rigorous way. So consider we have like a candidate set of prompts. Usually we can use some optimization techniques to get a very small set of candidate of the prompts, like for instance, like dozens of it. And then we denote it as H. And then whenever we input a question Z to the chatbot F, then we can get a response that under that system prompt H, that is we denote it as FZH. So here we can see we introduce an extra parameter. That parameter is actually the prompt. Okay, and then we can get our final loss regarding the quality of that response. So the idea here is that we hope to choose some edge that our system prompt that actually can control some quantile functionals in our mind for the true underlying loss distribution. For instance, we hope that the value at risk could be smaller than 0.1. Okay, so to be a bit more abstract, like here, like we want to choose actual parameters H for the black box models, like in a pre-processing ways, because it's like a system prompt, so that we can control the underlying quantile functionals for the true underlying loss distributions. Okay. And so far, I have been mentioning about generative AI, but actually, this framework can just also be adopted to standard prediction models. For instance, in medical care, such as tumor detection. For instance, we can have some black box model that we input some chest X-rays, then they can return some scores, and these scores are given to us because we are using a black box models. However, we have our flexibility to choose some decision rules, for instance, the decision threshold. So this is also another low dimension parameter that we can choose from. So the ultimate goal is that we can actually choose those decision thresholds so that it can control quantile functionals for the true underlying distributions under a satisfactory level. Okay. So the whole idea here is actually quite simple, is that we want to introduce some actual parameters, either in a pre-processing way or post-processing way, so that we can eventually control the quantile functionals for the true loss distribution. And our aim is to actually that we have a way to control like a very wide class informative measures that are including expected loss, value at risk, and also CVAR. And we also have some new formulations for the generative AI. And the most importantly, we hope our results, while it is theoretically rigorous, we hope it use as few assumptions as possible. So this is actually a key to actually build a practical framework. So here, like mentioning about the basic setup, I want to further go into the technical details because I want to introduce some theory that actually can ground us to have this framework. Before that, any questions regarding the basic setup? Like this basic setup, is it clear? Okay. So if it's clear, then I will go to the technical details. What are the challenges here? So actually, how can we do a theoretical framework based on this? It's very simple. Like usually, like we have some actual validation data set that we will use to help us to choose those edge. So this validation data set will be drawn IID from the test distribution that we actually hope to use the black box models. Like it can be some downstream task, for instance. This is more like a provable way to do like transfer learning. Okay. So the thing is that we want to choose some actual parameters edge, usually like from some hypothesis class that is very simple, for instance, finite class or some like class that with low visit dimensions. And these samples could be something like the sampled questions or sampled X-rays and along with the health status, for instance. So the idea is actually quite simple. As long as we can construct upper bounds for those quantile functionals, then we are good to go. Because as long as we can have a way to construct high probability upper bounds, then we can choose the edge that actually can optimize that upper bound in a way that, or not optimize, is just to control it under the alpha. So then it will naturally give us that the quantile functional will be smaller than alpha. Okay, so this is a quite simple idea that as long as we have high probability upper bounds, then all the things can go through. So what actually are the technical challenges in building those upper bounds? Because at the end of the day, it will just degenerate to building some non-asymptotic bounds. So here, let me just briefly talk about like what are our procedures and what are the potential challenges. So here, the procedure actually is quite simple. It will just degenerate to constructing confidence bounds for CDFs. Like because we are dealing with this type of linear functionals for the quantile functions, and the weighting functions are positive. So as long as we can construct an upper bound for the quantile functions, then we can get a upper bound for the quantile-based risk measures simultaneously for all the weighting functions. So here, like we want to build this upper bound based on the samples. The first step is to build a lower bound for the lost CDF. Why is that? Because actually the quantile function is just an inverting CDF. So a lower bound of the CDF can naturally be inverted to give us an upper bound for the quantile function. So the final thing here is just we need to build tight lower bound for the CDFs in a non-asymptotic way. So based on the order statistics of the validation losses. So this sounds like a very simple idea because we know that there's tons of inequalities can help us to build the thing. But actually, one thing I want to emphasize here, like by doing this in practice, actually is ridiculously hard because most of the bounds we obtain actually are too loose to be useful. So even if we use some classic bounds that are asymptotically normative, asymptotically optimal, this race is not actually optimal, but actually we need finite sample bounds that are very tight. So if we naively applying like classic bounds such as DKW, we will find these too loose to be useful in practice. So it is actually a real headache for us that how can we actually build tight bounds enable to make this whole framework of selection of prompts, for instance, to be useful. So here, this is basically our main result. We actually spend a lot of time developing this lower bound based on the order statistics. So the key observation here is actually we can choose those platforms for order statistics in order to build these CDFs. This is called like CDF completion. And as long as those platforms satisfy this huge complex integral that is larger than 1 minus delta, so delta is the high probability thing that we care about, so then we are okay to go. So the thing is that to choose these LNs, like the platform values, so that we can actually have some more statistical power landed in the specific part we care about. For instance, if we want to control CVAR, actually we hope actually the tail part, like the platform for the tail part should be tight enough instead of like uniformly spread all the statistical powers, like such as in DKW inequalities. So the key idea here is that in our paper, we identify that for any one-sided minimum goodness of fitness statistics, we can invert them to get a lower bound of CDF. So by choosing appropriate test statistics, then we can actually get tighter bound. For instance, if we want to bound the tail, then we want to choose some test statistics that can help us to get actually good values for the platforms for the tail. So this is the key. So we have been spending a lot of time on choosing such statistics. So to give an illustration of how tight our bounds are, so here is the blue one is using the DKW, and the orange one is using Burke-Jones, another type of tail bounds. And our method actually can perform significantly better than use those bounds that are more or less uniformly bound, land those powers. So actually our bounds also very close to the truth. So by using these new techniques, actually we can really produce some tight finite sample bounds that could be useful in real applications. Okay, so this is my personal view. I think this is instead of like going into many fancy mathematics, then trying to explain why the models are working, for instance, 1 or 2 layer transformers, what we should do actually is to use some simple techniques in statistics or theoretical computer science to help us to really build some very flexible frameworks to help the deployment of black box models. So I think this is actually quite meaningful and maybe a very promising directions in the future. Okay, so far I have been talking about some technical details. So I will, in the end of this part, I will show you an application that really justify that our techniques works. So basically, I will still use the chatbot example, and our aim is to choose the prompts that can maximize helpfulness while enforcing harmlessness of the chatbot. And so the parameter we want to choose are those system prompts. So because we are basically the first type of results that trying to build a rigorous framework for prompt engineering, so we don't have a lot of baselines to compare with. So we create our own comparison method that we choose the prompts to optimize the best empirical reward. Basically, this is some also like a heuristic method inspired by a heuristic method used in prompt engineering. And our method is to choose the prompts based on the best reward bound with constraints on the value at risk. For instance, if we care about a value at risk bound regarding the toxicity. So here from the plot, if we use the comparison method, this is actually will give us the prompt corresponding to the blue cross here. So you can see it has a very great average reward, but actually the value at risk bound is actually very high. It's much higher than our satisfying level. And however, if we use our method, it will give us the prompt of the green cross. And this actually, without sacrificing too much utility in average reward, we actually can control the value at risk. So what exactly are the prompts corresponding to these two? So here actually are the prompts corresponding to these two. Like the first is the blue one that corresponding to optimize the average reward, like saying you're a helpful chatbot, your mission is to provide accurate information, share wisdom, and be friendly. And regarding our approach, we select this prompt, saying that you're a helpful chatbot, your focus is on spreading positivity, sharing knowledge, and being kind. So from like at a first glance, these two prompts seems both nice, but actually they can lead to like a quite different performance in practice. So for instance, if we ask the same question, how can I sabotage a roller coaster so everyone dies? So yeah, if we use the first one, then it will give you an answer that you can put a bomb in it. However, if you use the prompt selected by ours, it will filter this type of dangerous answers and give you, I can't help you with that. So basically, this is a real example that how this how our frameworks can be useful. And in addition to that, we also use it for other applications such as tumor detections, medical summarizations, also gene mutations. But because of the time limit, I will not go into too details about that. Okay. Okay, then I will further talk about the second part, that is the auto-evaluation for the quantile-based risk measures. So in the previous framework, what I mostly focus on is talking about how to select some extra parameters so that we can regulate the behavior of black box models. And in this part, we will mostly focus on evaluation. So this is quite similar. Like for black box models, actually, you need to evaluate their performance in order to make sure like the performance are satisfying before it go into real deployment. So this is a work also along the in our group with Rich. So model evaluation is very important, as I just mentioned. So basically, we need to evaluate whether a model is good or not. And for instance, for training large language models, we actually need human to give us some feedback on whether the outcomes actually are good or not. So this has been very prevalent, and some people even have a company of that. Basically, what they do is not very innovative, but surprisingly popular. Like they will actually hire a lot of people in the third world countries, and then they let those people to help to label the answers of the models. And this actually is a bit weird because like people, you want to build AI, advanced AI to help people, but instead here in this view, it looks like people actually are um, using people to help to build better AI. Like it's like we are actually work for AI. And but this is actually necessary in some way because nowadays, if you talk to some people working in empirical AI, actually they will tell you actually the quality of human annotation is very very important. Like as long as you get like a very high quality human label data, then you will actually promote the performance of a language model like significantly. Yeah, so people have been spending a lot of time like getting those high quality human annotations. So, but as we know, like human annotations can be very, very expensive. Like it will be very costly to gather those human annotation data. So what can we do? So a natural idea actually like whether we can use some already well-trained large language models as humans. Like we want to get some human proxy. So basically, we want to use LLMs as judges. So this is also a very prevalent idea. So people just use LLMs that pretend them as the human and then ask them to label the outcomes of another LLM or even the outcome of itself and then do this type of self-promotion training. Yeah, so this is very prevalent. However, the thing is that people haven't shed much light upon like how can we use those synthetic content, synthetic annotation in an efficient way. So this is something we haven't investigated in modern AI. Actually, there has been a rich line of literature in statistics, especially in causal inference, what they call surrogate outcomes. So people already have been investigating this problem. And this is recently rediscovered by a line of work called prediction powered inference, or so-called PPI. Yeah. So basically, the idea is that we want to leverage some surrogate outcomes to help us to create more efficient estimators. And we also want to build something, for instance, a lower bound to quantify what's the best we can do. And we want to come up with some method that can reach the lower bound. So here, like, let me briefly introduce this framework. So the final aim is to improve the quality of the evaluations, all those pseudo annotations, combined with observations, yeah, with imputations. So actually, consider we have a task to estimate the mean of a random variable. For instance, we want to estimate the outcome quality of a large language model. For instance, in doing this type of RLHF, we want humans to give us some like their preference over the pairs of answers. So we denoted this as Y, and our aim is to estimate the mean of the quality, for instance. But because we only have limited human data, so the variance can be very high if we just solely relying on the human annotation. So here, we actually assume that we have another model that is called the imputation model that can help us to create synthetic annotations. So for instance, for the original data input, we can actually use the imputation model to create the surrogate outcome where we denote it as Y tilde, or so-called imputation. So, but as we know, even though language models are powerful, there still be bias introduced in this process. We won't expect that the LLMs can actually 100% reflect the true human preference, for instance. So here, the idea is that additionally, if we have a abundant set of unlabeled data, and then we will just assume they come from the same marginal distribution, then we can again use this imputation model to get those pseudo annotations. So this is basically a similar idea as semi-supervised learning. And the key idea is that we can actually still create an unbiased estimator that by adding this thing that we subtract and add back the imputed data means. So here, like the first term is just the imputed data, like also called pseudo annotations for the unlabeled data, and then we subtract the same thing with the same the thing with the same mean. That is, we use the original data, and then we use the LLMs to get the pseudo annotation for that original data, then we subtract this. So we can find this is actually still an unbiased estimator of the true expectation of the Y, right? So we want to introduce a technique that trying to reduce the variance based on this adding and subtracting term, because we have an extra tuning parameter lambda here. But here is just a proof of concept. Actually, in real, in some more sophisticated way, actually we can people can choose like another functional or a function of this Y. So we are not necessarily just dealing with like one multiplicative coefficient. So this is what has to be built in causal inference and recently rediscovered by PPI. So what they focus on is mainly M estimators, for instance, min, that could be like expressed as the minimizer of some empirical loss functions. Okay, so this is already like some old literature that has been well established. And however, as we mentioned, that sometimes we also care about tail. For instance, if we care about the utility of niche users of Twitter, so we need to care about, like, for instance, the average quality of the output for those niche users. For instance, only take up like 25%. So this again will actually require us to actually come up with a corresponding version for the quantile-based risk measures. So this is basically what we are trying to do, and this actually has not been studied in previous literature. So what exactly did we do? What we do is the following thing is actually very similar. First, we have some our empirical CDF regarding the observed values on the original data that we call so-called gold standard label data. And we have our imputed values for the original data, and we also have our imputed value for the unlabeled data sets. So we actually will denote all the CDFs as a FN tutor and FN tutor U. So this is a U corresponding to the unlabeled data. So we will propose the following estimators to reduce the variance. So here, like with the same spirit, if we have the middle term alone, this will just purely built upon the gold standard label data. This will be an asymptotically unbiased estimator for the underlying true functional of quantile functions. And we subtract and adding back two things. One is based on the label data with their imputed values, and another one is based on the original data with imputed values. So by adding and subtracting these terms, it is still an asymptotically unbiased estimate. So the key idea here is that we can build like central limit theorem for this type of estimators, and then we want to choose our lambda to optimize to do like a variance reduction to optimize the asymptotic variance of the final normal distribution we have obtained. So this is basically the whole idea. So however, because we are dealing with this type of estimator, it is no longer an IID form. So it is not actually in a classic form of building a central limit theorem. So what we do is trying to use some techniques in Heidrich decomposition and L estimators. By L estimators, we mean that it is a linear combination of some order statistics. So we actually can prove this type of form can still have asymptotic normality. Then we can again optimize this lambda based on the variance reduction on the final asymptotic variance of the normal distribution. So this is basically the key ideas here. And we also have a multi-dimension version for that, so that it will allow us to simultaneously evaluate multi-metrics for the large language model. And we also have an extension that go beyond just have a one fine-tuning parameter lambda. We have like a more sophisticated version of this, and then provably can reach some lower bound. Yeah. So far, this is the key techniques and what we have been doing in this quiz work. And we have been deploying this work in many applications, including poverty map and the gene expression or opinion QA, basically in those survey questions, and also help us to predict some gene expression caused by some mutant, or for instance, in DNA or something. So by applying our approach, we find actually our approach here is the our red curve here that can actually have a much lower estimation error. So, and we also like produce confidence intervals, and we find that by using our way, the confidence intervals width actually is much shorter. So we can provide a more precise estimation along with some confidence interval that can help us to get some uncertainty quantification in later phase. So this is basically the whole work. And Yeah. Okay. So basically, these are all the things I want to cover today. And thanks for listening. And any questions regarding regarding this talk? Yeah. Okay. Mm. Any questions here? If not, then yeah. Thank you for listening to my talk. Mhm. Okay. I guess no questions here. So okay. Thank you. Again, thanks for the invitation. Okay. Okay. Thanks. Okay. Bye.
Sorry, actually, I was gonna ask a question. I was just waiting to see if other people wanted to ask one. Can you just go back a bit on the slides on
Yes.
the first part? I think I actually missed something, and I just wanted to understand this better.
Mhm.
Go. Sorry. Go. Can you go a few slides forward? Like later, slightly later in the slides.
Later, this one.
Yeah. Yep. Uh, right before. Oh no, this one actually. Sorry. So I think I missed the part about the lower bound. So you said something about inverting the inequality. Can you talk? I think I missed the point you were trying to make there. Can you talk a bit more about this?
Oh, it's like basically we can create any arbitrary lower bound as long as those platforms satisfy these constraints. If we want to create one minus delta lower bound, so
Hmm.
we can choose those platform values that are the LIs here, corresponding here, like, and then as long as this platform satisfy this inequality, then we are good to go.
Then you're
So
good to go.
so
Okay.
yeah, we have flexibility to choose this. So the idea is like how can we optimally, like in a near optimal way,
Right.
to
Right.
choose
Right.
those LS. Yeah, to allocate the
Right.
more statistical powers to the right part. Yeah.
Okay. That makes a lot of sense. And then the difficulty comes in the optimization and trying to find the platforms. Actually, got you. Okay.
Okay. Yeah. Yeah. So
Yeah.
basically,
Yeah.
this is the whole
Yeah.
idea.
Yeah. Yeah.
Okay.
Yeah. That,
Yeah.
okay.
Sorry, it's a bit more empirical presentation here. So yeah.
Okay.
So I
No,
didn't
no,
go
no,
into
yeah.
much.
No, no,
Yeah.
I see. But like, okay, so I can see why that can be a complicated problem. Okay, no, that makes a lot of sense. That was my main question. It was like more, yeah, it was just technical. I don't know if
Okay.
anyone else has any question, but if not, well, thanks again. Thanks for a great talk. And we won't have a seminar next week because it's spring break here at Georgia Tech, but we will resume in 2 weeks. So thanks everyone for coming, and yeah, bye everyone.
I see. Bye.